Hey there. Welcome to our channel. We're so glad you're here. Please like, share, and subscribe to join us for awesome content. Also share this video with your family and friends. Let's get started. Imagine a swing in your backyard. The kind with creaky chains and a smooth wooden seat. The kind that obeys the patient push of your feet against the air. Now picture dipping that swing into a vat of golden honey, thick, slow, resisting every motion. The higher you try to go, the more the honey clings, dragging the arc of your flight into something languid, dreamlike. This is how time behaves when it stumbles into the grip of something massive. A star, a planet, or the most persuasive force in the universe. A black hole. Time doesn't stop. It stretches. It hesitates. You've felt this before in smaller ways. Waiting for a pot of water to boil, those last 2 minutes swelling into what feels like an hour. Or the opposite. When you're lost in laughter, and an afternoon slips by unnoticed. Time has always been flexible, even in your own bones. But out there, in the silent dark between galaxies, it bends in ways that defy intuition. Einstein called this time dilation, a gentle term for something so monumental. It means that time, the steady metronome of your life, is not so steady after all. It's more like a river, flowing faster in some places, slower in others. Near a black hole, where gravity pulls so hard that not even light can escape, time slows to a crawl. A single minute there could be a year back on Earth. But let's stay small for now. Let's stay with the swing, the honey. Because this is where relativity begins, not with equations, but with the ordinary. The way your shadow stretches longer at sunset. The way a train whistle sounds different when it's moving toward you versus away. These are hints that the universe is stranger, softer than it seems. Now picture this, you're holding two identical clocks. One stays in your hand. The other is placed on a mountain, where Earth's grip is just a little weaker. When you bring them back together, the mountain clock has ticked faster. Not by much, just a whisper of a difference. But it's enough to prove that time is not absolute. It breathes. It changes. And if time can bend on a mountain, what might it do near the edge of infinity? Somewhere in the cosmos, a star collapses into silence, and time folds in on itself like a sigh. Tomorrow you'll chase a beam of light and wonder where it's been rushing to all this while. Picture yourself running along a beach at dusk, the sand still warm beneath your bare feet. The horizon bleeds gold and violet as the sun dips lower, always just ahead of you, always slipping away no matter how fast you run. Now imagine, what if you could catch up to that sunset? What if you ran so swiftly that the light itself could not escape you? This was the daydream of a 16-year-old patent clerk named Albert Einstein. He wondered, if I could ride a beam of light, what would the world look like? The question seems simple, almost childlike. But within it sleeps a revolution. Light is the universe's most faithful messenger. It travels at a speed so constant, so unwavering, that it defies all intuition. Whether you stand still or race toward it at 1,000 miles per hour, light moves at the same relentless pace, 186,282 miles per second. Not a fraction more, not a whisper less. This is the first rule of light's quiet tyranny, and it unravels everything we assume about time. Here's the secret Einstein uncovered. To keep light's speed absolute, time and space must bend. Think of it like walking through a forest. If you must always step exactly 3 feet with each stride, as light must always travel at sea, but the ground beneath you suddenly softens into mud, what happens? Your legs compensate. Your stride shortens. The same is true for light, but instead of mud, it's space-time itself that warps. If you chase a beam of light, time slows for you to ensure light still outruns you at the same unflinching speed. The faster you go, the more time stretches like warm taffy. This is why astronauts on the International Space Station, hurtling at 17,500 miles per hour, age ever so slightly slower than those on Earth. A millisecond here, a millisecond there. But near light speed, a day for you could be years for someone else. Yet light is more than a speed limit. It's the thread stitching reality together. When you gaze at the stars, you're not seeing them as they are, but as they were. The light from Sirius, the brightest star in our night sky, left its surface 8 years before it brushes your retina. The Andromeda Galaxy? That soft smudge of light is 2.5 million years old by the time it reaches your eyes. You are, quite literally, looking into the past. And so Einstein's daydream becomes yours. If you rode a beam of light, the universe would contract before you like an accordion. Distances would shrink. Time would dissolve. Behind you, the cosmos would freeze into a single, eternal snapshot, a museum of moments you've outpaced. But here's the cruel twist. You can never reach light speed. The universe imposes a gentle veto. As you accelerate, your mass swells, requiring infinite energy to push further. Light remains the unattainable finish line, the horizon that forever recedes. Somewhere tonight, a pair of twins are born. One on Earth, one aboard a starship. By the time they meet again, one will have lived decades longer. Time, it seems, is a language only light speaks fluently. Imagine 2 children born under the same sky, their first breaths drawn in the same hospital room. They share the same face, the same laugh, even the same restless curiosity about the world. But one day, their paths diverge. One twin stays home, tending a garden where sunflowers turn their faces to the same patch of sky, year after year. The other twin boards a starship, a silver needle threading through the cosmos at nearly the speed of light. When the traveling twin returns decades later, stepping onto Earth's soil with legs unsteady from years of zero gravity, something is wrong. Or perhaps something is miraculous. The twin who stayed has grown old, hair silvered, hands mapped with veins and time. But the astronaut twin, they've barely aged a day. This is the twin paradox, one of relativity's most tender and unsettling ideas. Time has not cheated. It has simply unfolded differently for each of them, like 2 letters written in the same moment but delivered years apart. Why does this happen? Remember, time slows for those who move fast. The starship twin, racing through space at relativistic speeds, experienced time's flow as thick honey, each second stretched long and languid. Meanwhile, the earthbound twin lived in time's quick current, swept along by the planet's steady orbit around the sun. But wait, here's the rub. From the astronaut's perspective, it was Earth that hurtled away at incredible speed. Shouldn't the Earth twin then be the younger one? This apparent contradiction is the paradox's beating heart. The solution lies in acceleration. The starship twin didn't just move at constant speed, they had to turn around. That change in motion, like a car braking or swerving, breaks the symmetry. The twin who felt the forces of acceleration is the one who ages less. You've felt miniature versions of this. On a plane taking off, your body pressed into the seat as the world outside blurred. That push was a whisper of what the starship twin endured. A hint that motion doesn't just carry you through space, but through time itself. And so the paradox dissolves into a deeper truth. There is no universal now. The present moment is a local phenomenon, like sunlight pooling at your feet but not yet reaching the distant hills. The twins' reunion isn't a correction of time's error. It's proof that time was never absolute to begin with. Gravity, too, can lull time into slowing, like a hand pressed gently on a spinning top. Tomorrow, you'll stand on a mountain and feel the weight of the world bending the seconds around you. You stand at the base of a mountain just before dawn. The air smells of pine and cold stone, and the first pale light washes the peaks in gold. Somewhere above you, an alpine hut clings to the rocks, and inside it, a clock ticks, ever so slightly faster than the watch on your wrist. This is gravity's quiet work. Not the dramatic, crushing grip of a black hole, but the gentle persuasion of Earth's mass, bending time like a mattress indented by a sleeping child. The closer you are to something massive, the deeper you sink into the cosmic well it creates, the slower time moves for you. Imagine space-time as a vast, silken sheet stretched taut. Place a bowling ball in its center, and the fabric dimples. Now roll a marble along the edge of that curve. Its path bends inward, not because of some mysterious force, but because the floor of the universe itself has changed. This is Einstein's revelation. Gravity isn't a force that pulls. It's a slope that time and space create together. Your body knows this curvature, though your senses don't name it. When you climb stairs, your legs fight Earth's whisper of space-time bending. Each step is a tiny defiance of the cosmic slope. And just as a ball rolls faster down a steep hill, time runs quicker where gravity's grip is weak. This is why clocks tick differently. On a mountain peak, farther from Earth's core, time speeds up by microseconds each day. In a valley closer to the planet's weight, it slows. At sea level, you live in a compromise between sky and stone. Scientists measure this with atomic clocks precise enough to detect time stumble when lifted just a foot higher. GPS satellites must account for it, too. Their clocks, orbiting where Earth's grip is weaker, run faster than those on the ground. Without adjusting for this, your phone's map would misplace you by miles within minutes. But the true wonder lies in scale. Loving this? Hit that subscribe button to keep up with our videos. Also share this video with your family and friends. A white dwarf star, dense as a sun compressed into a moon, slows time to half speed at its surface. Stand there if you could, and while you experience a single minute, 2 would pass on Earth. Near a neutron star, time crawls like sap in winter. And at a black hole's edge, it nearly stops, a breath stretched into eternity. Yet here, now, the effect is tender. The difference between your head and your feet is a few trillionths of a second per lifetime. But it's enough. Enough to prove that time is not a river, but a chorus. And gravity is the conductor, slowing some voices, letting others soar. 2 clocks part ways. One stays on the ground, the other soars into the sky. When they meet again, their disagreement will measure the weight of the universe itself. Picture 2 identical clocks, their faces polished to a mirror shine, their gears whispering in perfect synchrony. They count seconds with the precision of a spider spinning silk, each tick identical to the last. Now imagine placing one on a desk in a quiet lab, while the other boards a jet plane to circle the Earth. When they meet again, they will tell different stories of the same journey. This is not science fiction. In 1971, physicists Joseph Haffel and Richard Keating did exactly this, flying atomic clocks aboard commercial airliners. The result? The traveling clocks disagreed with their earthbound twins by precisely the amount Einstein's equations predicted. Time, stretched thin by speed and gravity's absence, had slipped just a little, a few hundred nanoseconds lost to the sky. How does this happen? Let's break it into 2 quiet revelations. 1. The speed effect. The faster you move, the slower time flows for you. Like a dancer spinning so fast the world blurs. The jet's velocity, though mere drops in the ocean of light speed, still nudge time into slowing. 2. The gravity effect. At cruising altitude, farther from Earth's core, gravity's grip weakens. Here, time speeds up, like a clock placed on a higher shelf in gravity's cupboard. The Haffel-Keating experiments saw these effects wrestle. Eastward flights, moving with Earth's rotation, adding speed, slowed time most. Westward flights, against rotation, saw milder changes. All airborne clocks ran faster than ground clocks. Gravity's influence won. Atomic clocks measure time by counting the vibrations of cesium atoms, 9,192,631,770 ticks per second, unchanging as a heartbeat. That such precision can still detect time's bending proves relativity isn't abstract math. It's the hidden rhythm of reality. Your phone knows this truth. GPS satellites orbit 12,550 miles up, where time runs 38 microseconds faster daily than on Earth. If uncorrected, this would skew your location by miles within minutes. Engineers must bake relativity into the code. Your maps are proof Einstein was right. Somewhere above you right now, a satellite's clock ticks faster than your wristwatch. While deep in space, a black hole's gravity grinds time to dust. Tomorrow, you'll peer over the edge of that infinite slowing. Imagine standing at the edge of a waterfall, not one made of water, but of time itself. The closer you step to the brink, the slower your seconds flow, until at the very edge, they stretch thin as candle smoke. This is what happens near a black hole. Time doesn't just slow, it gasps. It hesitates. A black hole is born when a massive star collapses, its gravity growing so strong that not even light can escape. The boundary where light's struggle ends is called the event horizon, a point of no return. But something stranger happens here. To an outside observer, time for an object falling toward the black hole appears to freeze completely at the horizon. The object's last visible second stretches like taffy across eternity, its image reddening and dimming as light fights the pull. Yet, for the falling object itself, time passes normally. If you were the one falling with some magical shield against being torn apart, you'd cross the horizon in finite time, noticing nothing special, while to someone watching from afar, your descent would appear to take forever. This paradox reveals time's deepest secret. It is not universal, but personal. Your now is not mine if we move differently or feel different gravity. Near a black hole, this effect becomes extreme. Consider the supermassive black hole at our galaxy's heart, Sagittarius A star. If you orbited just outside its event horizon, for every hour you experienced, years might pass on Earth. You could watch civilizations rise and fall in the time it takes to drink a cup of tea. Return to Earth, and everyone you knew would be dust. Black holes don't just bend time, they shatter our intuition about cause and effect. Inside the event horizon, all paths lead toward the singularity, the black hole's heart. Time and space swap roles. Just as you can't avoid moving forward in time outside a black hole, you can't avoid moving toward the center inside one. Yet even black holes aren't eternal. They slowly evaporate via Hawking radiation, a quantum whisper at their edges. Over trillions of years, even these monsters will fade, their final moments ticking away like a forgotten clock in an empty universe. Somewhere tonight, an astronaut drifts toward sleep aboard a spaceship, dreaming of home. While on Earth, decades flicker by like pages in a book. Tomorrow, you'll open that book to the story of the astronaut's diary. You float weightless in your cabin, pressed against the observation glass like a child at a candy store window. Earth hangs in the blackness below, a blue marble streaked with white. But something is wrong. With each orbit, the planet beneath you seems to quicken. Clouds swirl in fast forward. Continents cycle through seasons in hours. The lights of cities bloom and shift like time-lapse stars. Your heartbeat, steady in your ears, marks time at its usual pace. But Earth is spinning too fast, like a child's top winding down. This is relativity's cruelest gift. The faster you travel, the more you leave time behind. Imagine this diary entry, written in the quiet between engine hums, Day 1378, aboard the SS Relentless. Today, Mission Control confirmed what I've been seeing. For every day I experience at near light speed, a full year passes on Earth. I watched the annual pulse of Christmas lights across Europe, 7 flashes in 7 days. My daughter was 6 when I left. She turns 13 tomorrow. My tomorrow. Her today. This is the human heart of time dilation. Not just ticking clocks, but ticking lives. The astronaut's tragedy mirrors the twin paradox, but with higher stakes. Not just years lost, but relationships, memories, the very fabric of home. Biologically, the astronaut barely ages. Their cells divide slower in this slowed time. A 5-year mission could mean returning to find their great-grandchildren older than they are. The science is sound. At 90% light speed, 1 ship year equals 2.3 Earth years. At 99.9% light speed, 1 ship day equals 1 Earth year. At 99.9999% light speed, 1 ship minute equals 1 Earth year. But numbers can't capture the loneliness. The way a voice message from Earth grows more distant with each reply, your good morning, answering their good night, from years past. How do you say goodbye when your soon is someone else's never? Yet there's wonder here too. The astronaut becomes a time traveler, however unwilling. Their journey sketches a map of humanity's future. They might leave during war, return to peace, depart with fossil fuels, arrive to fusion, launch to a full Earth, come home to colonies on Mars. The ship's hull becomes a lens, bending not just light but history itself. Back on Earth, a physicist adjusts a telescope, not to see stars, but to hear them. The universe, she realizes, doesn't just stretch time. It sings it. Close your eyes. Imagine the universe not as silent emptiness, but as a grand concert hall. One where every star, every planet, every speck of dust hums with its own vibration. Time here isn't a steady metronome, but a melody shaped by the instruments around it. A black hole's gravity drags the tempo like a deep cello bow. A passing comet adds a staccato flourish. This is relativity's hidden music. Spacetime itself is the score, and matter the musician. You can hear echoes of this symphony in the most precise clocks ever built. Atomic clocks, so sensitive they'd lose just 1 second every 300 million years, actually change their rhythm when a storm cloud passes overhead. The extra water weight bends time. The moon reaches perigee. Its stronger pull slows the ticks. You simply lift the clock onto a table, farther from Earth's core. These variations are tiny, nanoseconds per day, but they prove that time doesn't just pass. It responds. Like a violin string trembling when a flute plays nearby, space-time vibrates to the mass and motion around it. Now expand the scale. Picture our solar system as a musical ensemble. Jupiter, the bass drum. Its massive gravity tugs Mercury's orbit, creating a 43 arcsecond wobble in its path. Einstein's first proof of curved spacetime. Neutron stars, the cosmic metronomes. Their precisely timed pulses slow when passing behind other stars, revealing warped spacetime like a shadow across sheet music. The Milky Way's black hole, the sustained pedal tone. Its gravity makes nearby stars dance in sped-up orbits, their light reddening as they struggle against time's drag. Even empty space contributes. Quantum foam, the seething potential at the smallest scales, may make time choppy at intervals of 10 to the power of -43 seconds. The Planck time. It's as if the universe is humming below the range of hearing. But the true wonder comes when you realize you're part of the performance. Every step you take, every breath, subtly alters spacetime's composition. Your mass, small as it is, adds to the local gravitational field. When you climb stairs, you change your relationship to Earth's tempo. You are, in the quietest way, a musician in the cosmic orchestra. Your life a brief, bright note in a song 13.8 billion years long. Somewhere beyond our galaxy, two black holes spiral toward collision. Their final duet will send ripples through the fabric of time itself. Tomorrow, you'll learn how to listen for the echoes of such ancient dances. You stand before a control panel glowing with soft blue light. A single lever rests under your palm, its surface cool and smooth. This is no ordinary switch. It's a dial for time itself. Push it forward, and your ship's engines will hurl you through space at ever-increasing speeds, where relativity's mathematics promise a strange gift. The slower your clock runs, the more you outpace time on Earth. At 87% light speed, the equations whisper their first secret. For every day you experience, 2 pass on Earth. At 99.99% light speed, 1 of your minutes equals 1 Earth week. At 99.9999999% light speed, a single breath could span years back home. The numbers paint a tantalizing picture, a way to stretch subjective time like taffy, to live years while the universe ages centuries around you. But as your fingers hover over the controls, deeper questions surface like bubbles in a pond. What does living even mean at such speeds? Your body would obey relativity's rules perfectly. Your heartbeat wouldn't quicken. Your thoughts wouldn't race. Your morning coffee would cool at the same leisurely pace. To you, everything aboard the ship would feel normal. The distortion only appears when you look outside. When Earth becomes a streaked blur, its broadcasts stretched into whale-song slowness. Yet practical barriers emerge. 1. Energy. Reaching 99.9% light speed requires more fuel than exists on Earth. 2. Navigation. At such velocities, hydrogen atoms become cosmic bullets, each impact like a particle accelerator beam. 3. Psychology. How does a mind process watching civilizations rise and fall between breakfast and lunch? Perhaps the most haunting limitation is causality's curtain. No matter how fast you fly, you can never outrun your own past. The light from Earth's history will always reach you in sequence, just increasingly delayed. You might see the pyramids being built through your telescope, but you can't return to walk among them. Still, the dream persists. In particle accelerators, muons, heavy cousins of electrons, routinely experience this time dilation. Their normal 2.2 microsecond lifespan stretches to minutes when moving near light speed. long enough to reach detectors that would otherwise never spot them. Nature proves it's possible, just not yet for anything as complex as a human. As you release the unused control lever, its glow fades like a dying star. Back on Earth, a child skips a stone across a pond, each ripple a tiny echo of spacetime's flexibility. Tomorrow, you'll learn how even your footsteps bend the universe. Just a little. You stand barefoot by a still pond at twilight, the water's surface smooth as polished obsidian. A pebble rests in your palm, worn smooth by centuries of rivers, small enough to disappear between your fingers. When you drop it, the impact sends ripples cascading outward in perfect circles, each wave carrying the memory of that single moment into the far reaches of the pond. This is how you bend spacetime, not with the crushing gravity of a star or the terrible hunger of a black hole, but with the quiet, persistent fact of your existence. Every atom in your body, every thought in your mind, gently presses into the fabric of the universe. The mathematics say so. Your mass, about 70 kilograms, curves spacetime around you by 0.00000000000000000001%. When you climb stairs, you create a time difference of 0.0000000001 seconds between steps. Even your beating heart generates minute gravitational waves. These numbers seem laughably small, but consider, the same equations governing your subtle influence also describe colliding neutron stars and the birth of galaxies. You are made of the same stardust, playing by the same cosmic rules, just on a gentler scale. 3 quiet truths emerge. 1. You are always time traveling. Right now, as you read this, time moves slightly faster for your head than your feet, by about 0.000000000003 seconds per year. You're living Einstein's theory in your bones. 2. Your choices create tiny branches in spacetime. That decision to turn left instead of right, it altered the gravitational pull on every atom around you, an infinitely small but real change in the universe's configuration. 3. You're entangled with everything. The gravity from your outstretched hand reaches the Andromeda Galaxy, just as its stars, 2.5 million light-years away, tug on you. The connection is weak, but unbreakable. As night deepens, the pond's ripples fade, but their energy hasn't disappeared. It's just dispersed, mingling with the water's constant molecular dance. So too with your mark on spacetime. The chair you sat in today, the air you exhaled, the gravitational imprint of your walk home. All these perturbations endure, woven into the universe's history. Einstein called this spooky action at a distance. You might call it comfort, proof that existence is never passive, that to live is to constantly reshape reality, however slightly. The last ripples vanish as the pond stills, reflecting the first stars. Somewhere above, a satellite measures time's flow, and in its precise ticks, there echoes the faint, endless rhythm of your place in the cosmos. Thanks for watching. Please subscribe, like, and share. See you next time.